The introduction of this scientific paper discusses the study of the ordered assembly morphologies of Diblock copolymers on the same substrate. The self-assembling, SAW, and directed self-assembly, DSA, of block copolymers, BCPs, have gained attention for their potential in advanced photolithography for semiconductor devices. Highly ordered assembly morphologies, such as cylinder and lamella, have been achieved in thin films of BCPs without the need for additional topcoat materials. The introduction also highlights the development and advantages of BCP self-assembly in creating highly ordered nanostructures, which have been applied in various electronic devices. DSA lithography using BCPs relies on guiding patterns to induce the self-assembly of BCPs into well-registered nanopatterns. The pitch size of the BCP nanostructure is determined by parameters such as the degree of polymerization and the Flory-Huggins parameter. The successful combination of bottom-up and top-down approaches in nanopatterning has garnered attention. The specific block copolymer used in this study is polystyrene B polymethylmethacrylate, PSBPMMA, which can form lamellar and cylindrical morphologies. These morphologies have been utilized as etching masks for the fabrication of various nanostructures. The study aims to investigate the SAW and DSA morphologies of two different types of D-block copolymers on the same silicon substrate. The experimental research includes the preparation of the BCP thin films, the orientation of microdomains, and a theoretical analysis. The use of electron beam lithography, EBL, allowed the preparation of silicon substrate grooves with different widths and depths. The surface energy of the substrate was engineered to achieve perpendicular or parallel alignment of the BCP microdomains. The study also analyzed the line, spacing width of nanowires in relation to the groove structure. Overall, the introduction emphasizes the potential of BCP self-assembly in advanced lithography and electronic devices. The study aims to provide insights into the assembly morphologies of D-block copolymers on the same substrate and establish an optimized process for specific self-assembly. The results and discussion section will provide further details on the experimental methods and findings of the study. Schematic diagram of the self-assembling process flow of PSBPMMA1 lamellar domains and PSBPMMA2 cylindrical domains. The process involves cleaning the C substrate, neutralizing the surface with a polymer brush, spin coating the BCP solution, and achieving microphase separation through thermal annealing. SEM images of the optimal PSBPMMA1 thin films by vacuum thermal annealing at 240 degrees Celsius for 4 minutes. The images show perfect self-assembly microphase separation patterns without defects, indicating the effectiveness and stability of the vacuum annealing conditions. Water contact angle measurements of the C substrate before cleaning, after substrate cleaning, and after grafting the PS brush. The measurements demonstrate that the surface becomes hydrophobic after grafting the PS brush, which is essential for achieving the desired self-assembly patterns. Statistical analysis of the film thickness with different rotation speeds of PSBPMMA1 and PSBPMMA2. The data show that the film thickness remains constant at a certain spin coating speed, indicating the importance of controlling the film thickness for achieving the desired self-assembly morphology. SEM images of the film thickness of PSBPMMA1 and PSBPMMA2 after etching. The images show the removal of the surface PS block layer in phosphorus monosulfide BPMMA1 and the visibility of PMMA cylinders in phosphorus monosulfide BPMMA2 after accurate control of the film thickness. SEM images of the PSBPMMA2 film annealed under different conditions. The images demonstrate defect-free cylindrical microdomain patterns under different annealing temperatures, indicating the optimized conditions for achieving microphase separation of PSBPMMA2. Schematic illustration of the DSA process of PSBPMMA2 with graphoepitaxy. The process involves the use of grooved substrates to achieve precise directional alignment and parallel alignment of the BCP nanostructures. SEM images of the PSBPMMA2 directed self-assembly in topographic confinement with different groove widths. The images show different parallel cylinder phases and the effect of groove width on the alignment and pattern formation. SEM images of the PSB-PMMA1 directed self-assembly in topographic confinement with different groove widths. The images demonstrate the perpendicular alignment of lamellar microdomains to the trench sidewalls and the trench bottom, indicating the successful achievement of desired self-assembly patterns. Nanowire width variation of directed self-assembly of PSB-PMMA2 and PSB-PMMA1 in a 360 nm grooved substrate. The data show the uniformity and accuracy of the nanowire width measurements, indicating the high quality of the directed self-assembly process. In conclusion, this study demonstrates the successful fabrication of self-assembly microphase separation patterns of PSB-PMMA1 and PSB-PMMA2 thin films using optimized vacuum thermal annealing conditions. The results show defect-free patterns with high resolution and repeatability. The use of specific polymer brushes and control of film thickness are crucial for achieving the desired self-assembly morphology. The DSA process with graphoepitaxy allows for precise directional alignment and parallel alignment of the BCP nanostructures. The results highlight the potential of BCP thin films as pattern templates for nanowire array fabrication in advanced semiconductor devices. This work focused on studying the self-assembly and directed self-assembly (DSA) morphologies of two different block copolymers, BCPs, on brush-modified C substrates. The researchers investigated the effects of various process conditions, such as BCP concentration, substrate cleaning, brush grafting, BCP film thickness, annealing temperatures and durations, and substrate groove widths, on the self-assembly and DSA behaviors of the BCPs. They found that by modifying the substrate grooves with different brushes, different morphologies could be achieved through DSA using the graphoepitaxy method. The researchers also analyzed the mechanisms behind the orientation of cylindrical domains along trench sidewalls and the orientation of lamellar microdomains perpendicular to trench sidewalls and the trench bottom. The study provided valuable information on achieving low defect density and high productivity in self-assembly and DSA processes, which is important for large-scale manufacture in future semiconductor devices. The authors declare no conflicts of interest and acknowledge the support of the National Science Foundation of China. If you are an author or copyright holder for the work presented in this video and you have any issue with the existence or contents of this video, please let me know.